Welcome back. In Module 1, we laid the foundation, binary arithmetic, numeration systems, logic gates, memory devices, and basic programming. In this module, we are going deeper. We'll take the building blocks we've already explored and learn how to combine, optimize, and control them. You'll see how real-world systems handle complexity, speed, and accuracy. On the programming side, we'll master control statements, repetition structures, logical operators, and program design techniques that match how hardware operates. The goal is to make you comfortable designing both the hardware logic and the software logic for a complete system, whether that's a traffic light controller, a digital clock, or a sensor monitoring program. Canal mapping simplifying logic. One of the most important tools for a digital designer is canal mapping, or K-maps. A K-map is a visual method of reducing complex logic expressions to their simplest form. The idea is simple: the fewer gates we use, the less space the circuit takes, the lower the cost, and the faster it operates. In practice, you map out the truth table of your logic function into a grid, then group the ones together in patterns. These groups translate into simplified expressions. In software terms, it's like optimizing an if-else chain into a smaller, cleaner set of conditions so the program runs faster and is easier to maintain. While hardware designers use K-maps for physical optimization, programmers can apply the same principle to reduce redundancy in logical conditions. Encoders and decoders, translating between codes. An encoder takes multiple inputs and turns them into a smaller number of output lines, producing a binary code that represents the active input. A decoder does the opposite: it takes a binary code and activates a specific output line based on that code. In hardware, these are used in keyboards, display systems, and communication circuits. In OBasic, we might implement an encoder by mapping several possible inputs into a smaller set of codes, or a decoder by using conditional statements or arrays to activate specific actions based on an input code. Troubleshooting logic circuits. As circuits grow more complex, troubleshooting becomes essential. Common issues include incorrect wiring, faulty components, or timing mismatches between signals. In software, similar issues occur: logical errors, incorrect variable values, or unexpected timing in event-driven code. The troubleshooting mindset is the same for both. Start by checking inputs. Confirm each intermediate step. Verify that outputs match expectations. In OBasic, this might mean printing variable values at key points or using the debugger to step through the code. In hardware, it might mean probing signals with an oscilloscope or logic probe. Advanced binary math circuits. While simple adders and subtractors are fundamental, more advanced binary circuits handle multiplication, division, and even more complex operations like square roots or trigonometric functions, often as part of an arithmetic logic unit, ALU. In software, OBasic can perform these operations directly using arithmetic operators or built-in functions. The difference is that in hardware, speed and efficiency depend on the logic design, while in software, efficiency depends on both the algorithm and how the compiler turns it into machine instructions. Multiplexers and demultiplexers in complex systems. We introduced this in Module 1, but in more complex systems, multiplexers can be cascaded or used dynamically to route data between many sources and destinations. Demultiplexers can be combined to distribute signals in patterns, such as in large display panels. In OBasic, this maps directly to controlling data flow in your code, deciding which data source to read from, or where to send output, based on control variables. Timers and counters, coordinating actions. Timer circuits in advanced systems often involve programmable timers that can produce variable delays or generate periodic interrupts. Counters can be preset, count up or down, and trigger actions when a specific count is reached. In OBasic, you can simulate these behaviors with loops and time functions. For example, using a loop with a time check to blink a message every second is a software equivalent of a hardware timer controlling an LED blink. Analog to digital conversion in practice. In a real system, ADCs must sample signals at a certain rate and with a certain resolution. A slow sample rate might miss important changes, while a low resolution might not capture enough detail. In programming, once you receive ADC data, you may need to scale it, filter it, or process it further before using it. OBasic can read in such values, perform calculations, and even simulate the ADC process if you're testing without real hardware. Control statements in OBasic. Control statements are the software equivalent of logic design in hardware. Just as hardware gates control signal flow, control statements decide which parts of a program run under certain conditions. Selection statements like if, else, or select case let you choose different paths based on conditions, similar to how a decoder activates different outputs. Repetition statements like for, while, and do, loop repeat actions, similar to hardware counter stepping through operations. Nested control statements allow you to combine these structures, creating decision trees and loops that handle complex tasks. Equality, relational, and logical operators. These operators are the backbone of making decisions in software. Equality operators check if values match. Relational operators compare values to see which is larger or smaller. Logical operators like and, or, and not combine or invert conditions. The hardware analogy is direct. Equality comparisons are like XOR gates checking for differences. Relational comparisons might be implemented with comparator circuits, and logical operators are just the logic gates we discussed earlier. Loop control and flow changes. Sometimes you need to break out of a loop early or skip to the next iteration. In OBasic, exit lets you leave a loop, while continue jumps to the next iteration. In hardware, similar effects are achieved by disabling a clock signal to a counter or resetting a sequence. Top-down design and stepwise refinement. When designing either hardware or software, starting with the big picture and breaking it down step by step is critical. In hardware, this means starting from the overall system diagram and breaking it into blocks like input processing, control logic, and output. In OBasic, you start with the main tasks your program needs to accomplish, then refine them into functions, loops, and conditions. Integrating hardware and software in a project. Let's imagine building a digital temperature monitoring system. The hardware includes a temperature sensor, an ADC, and a display. The software, written in OBasic, reads the ADC data, converts it to temperature units, and updates the display. If the temperature crosses a threshold, the software triggers an alarm output. In this scenario, hardware logic ensures accurate sensor reading and stable signal conversion. Software logic handles user interaction, calculations, and decision-making. The two sides work together seamlessly because the designer understands both. Final thoughts. By now, you should be able to think in both hardware and software terms at the same time. You can see a problem and decide which parts belong in circuitry and which parts are better handled by code. You can optimize both for speed, cost, and reliability. This dual perspective is powerful. Whether you go on to design embedded systems, control automation, or custom software tools, you'll be equipped to handle the full stack, from the electrons moving through a transistor to the objects and variables moving through your program. And remember, in the world of digital electronics and programming, your creativity is the limit.